In this video, we will be learning the inner workings of one of the most popular transformer architectures that exist today. LLMs like DeepSeek, Mixtral, and there's also a rumor that GPT-4 as well all use this special architecture, the mixture of experts. We will learn what these mixture of experts models are, how they operate, some variants of this idea, and terms like sparse mixture of experts and switch transformers and many more. And as I walk you through all of these concepts, I will also show some simple code snippets that should explain to you line by line how it all works and comes together. I have always wanted to make a video like this on mixture of experts, and I think it's one of the most relevant and coolest concepts in today's LLM research. Especially after the recent success of DeepSeek, I thought this is as appropriate a chance as I'm gonna get to highlight one of the architectural reasons behind DeepSeek's success. This video will start off with simpler concepts and we will gradually build towards more advanced things and codes as the video goes on. As usual, do leave a comment if you have any question, and you can also reach out directly on my Patreon. As a reminder, all the material used in this video will be available via Patreon, so do check out our Patreon link below. You guys are magnificent. Let's get started by discussing the main idea behind mixture of expert models. So when you input any text into a large language model, it first splits it into a sequence of tokens. In general transformers, all the tokens are processed by the same shared computational graph in the network, meaning that there is a fixed set of weights and operations that are applied to each of these input tokens to process them. The idea of mixture of experts challenges this very concept. What if instead of processing every token through the same computation graph, we can somehow have multiple smaller networks that are experts at processing specific types of tokens? Given a specific token, we will then need to determine which expert or experts are best to process it and then route those tokens through those selected experts. Maybe tokens related to coding is routed through one expert, tokens related to math is routed through another, tokens related to syntax is through one more expert. This process of assigning tokens to specific experts is also called routing. We are going to talk more about how to implement some of these concepts, but first, let's talk about the benefits of an architecture like this. Well, one benefit is multi-device parallelism at inference time. Suppose you have multiple GPUs. You can place individual experts in different devices and parallelly process the sequence across multiple devices. Another advantage is that it reduces the active weights used during inference time. Suppose you have 8 experts, but you only activate or route through 2 experts at a time for each token. Well, this means that we don't spend any compute processing the other 6 experts for that token. This means that the number of floating point operations per token are significantly reduced. For DeepSeek V3, you can see that they have 671 billion parameters in total, but only 37 billion parameters are activated per token. One point of clarification here is that when running inference, your entire model still needs to be in memory. This means you have to load all of the experts into your GPU, even though you're going to use selected GPUs and selected experts for specific token processings. So mixture of experts don't reduce the total memory required to train or store the model. It reduces the number of weights activated during inferencing by load balancing the computation across multiple experts and multiple devices. In the next section, we will do a quick review of the basic architecture of a normal LLM and then point out where exactly this mixture of expert idea can be implemented. And later on, we will see some code snippets to explain all those ideas we talk about more concretely. Let's go. Alright, so let's say a batch of tokens of shape b, s are inputted into a LLM. B is the batch size and s is the sequence length. Well, first, these tokens are converted into embeddings using an embedding layer, resulting into a 3D matrix of shape b, s, d, where d is the embedding size. You can just imagine this tensor containing vector representations for each token in your input batch along each sequence. So for example, if you're inputting 2 sentences in the batch containing 10 tokens each with an embedding dimension of 100, your tensor will be shaped 2, 10, 100. Once inside the transformer decoder, these 3D token embeddings pass through several decoder layers. Each decoder layer has 3 components: a causal masked attention layer, a feed-forward dense neural network, and a final residual connection. The causal masked attention layer applies attention to contextualize each token with every other token that appeared previously in the sequence. Basically, in the beginning, each token in the sentence is embedded independently of each other. They don't have any knowledge about each other. But the attention layer introduces every token with every other token that appeared before it and creates new contextualized representations by mixing information from the entire sentence. These new set of embeddings are then passed through a single feed-forward neural network. The task of this feed-forward network is to just transform the new token representations and add more non-linearity before passing them onward to the next layer. This operation does not combine information across different tokens in the sequence like the attention layer did, and that is why they're also called pointwise feed-forward neural nets. We first flatten the 3D tensor from the shape b, s, d to a 2D tensor of shape b times s, d, and then pass this flattened 2D tensor through the dense layer. So basically, from that previous 2, 10, 100 tensor, you flatten it to 20, 100. The dense layer projects each embedding individually and outputs the new representation. This tensor is once again reshaped back to the original 3D dimension of shape BSD. Finally, the original input is added back to the output as a residual connection. Well, residual connections have a lot of advantages in deep learning, like allowing smooth gradients to flow through really deep neural nets and allowing networks to learn residual information instead of transformative information. In my history of convolution network video, I talk more about the concept of skip connections and resnets, but we don't really need to go too deep into residual connections for this video just yet. So a transformer decoder just represents this specific decoder block one after the another. The same 3 steps: attention, feed forward, residual connection. Each decoder layer just contextualizes the input sequence more and more and adds more information to the tokens and prepare it for the final output. The basic skeletal code for the transformer model looks something like this. You input a sequence of tokens, convert it into embeddings to get floating point vectors, and then pass it through a series of decoder layers. Each decoder layer first applies multi-headed attention, flattens the 3D to 2D, and apply the feed-forward layer. Then reshape it back and create the final residual connection. If you need more information about attention, transformers, and language models in general, we have plenty of videos in our channel for concepts as well as code. So feel free to jump to any of these videos after you're finished with this one. In the next section, although, we will finally get to implementing a basic form of mixture of experts, the dense mixture of experts. So, whenever people say mixture of experts, in most cases, they are referring to replacing the feed-forward component with a gating network. Remember, the feed-forward layer inputs token embeddings of shape b times s, d and projects each token embedding through a single neural network. The dense mixture of experts replaces this one neural network with a bunch of neural networks called experts. Let's take an example where our LLM trains 3 experts. When processing one token, we first need to figure out how much influence should each expert have on processing this token. This influence score is often called the expert probability score or the token to expert affinity score. We are just going to call it the expert probability for the rest of this video. To determine this probability, we will train a separate network called the router network. The router network is a simple feed-forward network which inputs a token embedding and outputs a probability distribution over our experts. Because it's just a feed-forward layer, we can input our 2D BS, D tensor and receive the probability distribution for each token over the experts as highlighted in this diagram. Going forward, I'll just call BS as T, representing total tokens. Instead of saying BS, this, that all the time, I'll just call it T, D. For a dense MOE, which is the most simplest form of MOE as introduced in this paper, we pass all of the T tokens through each expert. And finally, we do a weighted average of the router's output probability with the new embeddings. So if the router output for a specific token has a high value, say 0.8 for expert 2, that expert also has 0.8 times contribution to the final embedding. By doing this weighted sum over all experts, we finally get back our desired T, D embeddings, which is exactly what the previous feed-forward layer from the vanilla LLM was giving us. And just like that, we have replaced a feed-forward layer with a dense MOE. Dense MOEs are considered more expressive than vanilla feed-forward layers in general because using multiple experts like that can give the LLMs more freedom to represent the input sequences. Like depending on the type of the input tokens, different experts can step up and influence the final embeddings more strongly. Also, this is called dense because all the experts are being processed at all the times and they all contribute to the final embedding. But the problem with dense MOEs are that we don't really save up on any computation because again, all experts are being processed at all times for all tokens. In the next section, we will talk about the more popular variant called sparse mixture of experts, which addresses this limitation. But before that, let's take a short look at how to code something like a dense MOE. So this was the original code for the transformer model, right? Remember that the mixture of experts only impacts one section of the transformer. It just replaces the feed-forward layer inside the decoder. So we can keep everything here as is, and instead of using these feed-forward layers, we'll just use a dense MOE layer. The dense MOE layer, just like the feed-forward layer, will input all the token embeddings of shape T, D, apply point-wise transformations, and output a new embedding of shape T, D. Let's have a closer look at how to code the dense MOE layer now. Well, first we create a list of E experts. In this example, each expert is just a simple feed-forward layer with just 2 MLP layers. Next, we create the router network. The router network also has 2 MLP layers, but its final layer has E neurons. Notice that we have the softmax operation in the end here, which guarantees that the output will have a probability distribution over all of the E experts. Then we pass the input through each of the E experts, getting the unscaled outputs for each expert. The shape of these concatenated expert outputs is T, E, D. Lastly, we scale these outputs by the probabilities as outputted previously from the router and then add them all together along the expert dimension. Even if the code looks a little bit complicated, this is just a form of a weighted average where higher affinity experts will influence the final embeddings more strongly than lower affinity experts. Also, by the way, all the slides, all the codes used in this video will be available in our Patreon, so make sure you check it out. If you're liking this video, please do hit the like button and subscribe to the channel. And as always, a huge shout out to our current channel supporters. You guys are truly magnificent. Thank you for financially supporting the work we do at this channel. Thank you so much. Back to the video. In this section, let's look at sparse mixture of experts or SMOE. As highlighted previously, the issue with dense MOEs are that we're not really reducing any computations for the model, because all experts are always being executed no matter what the tokens are. Even if you got one expert whose router value is just very small, like 0.01, that will still be processed despite not really making much of a difference in the final embedding. Well, enter Sparse MOE. The simplest form of Sparse MOE is where you just pick the highest probability expert and only process that. This can be done very easily. You can just take the argmax of your router probabilities, and that will give you the indices of the experts that has the highest probability for each token, and then just execute whichever expert that was picked for each token. The code is pretty simple. Here we loop through all of the experts, find the tokens whose router had chosen expert I as the highest value, and only pass this smaller subset through the expert I, and finally combine the different tensors back together to output the final tensor. And in this version, we just execute one expert per one token. It all sounds very fine and dandy, but unfortunately in practice, this single expert version of Sparse MOEs almost never work. These methods fall prey to something known as router collapse, where the router often just ends up choosing a single expert over and over again for all tokens and fail to utilize all of the resources and all of the experts equally. This is a classic case of the exploration versus exploitation dilemma. The model needs to pick different experts sometimes to be able to determine which experts work best for which types of tokens. This is why in this seminal MOE paper, it was proposed that you have to route each token across at least 2 experts for the network to be able to compare results and make a decision. The code is also surprisingly simple. Here, after getting the token to expert probability scores from the router, we use torch.topk to find out the top 2 highest probability experts for each token. This is going to be an integer tensor of shape t, 2, where the top 2 expert IDs for each token is present. Then we run a for loop through our E experts and process the tokens allotted for each expert. In practice, we actually run this parallelly across multiple GPUs, but this for loop implementation is much easier to explain and to understand. So for this video, I'm just going to continue to present it like this. For each expert, we first figure out which tokens have the current expert in their top 2. This equal operation identifies which row in the selected index tensor the current expert occurred in. We get a tensor of booleans, and passing that through the non-zero function tells us which tokens need to be routed to this expert. So here, token 1, 5 need to be routed through expert 1. These tokens are processed by the experts, and their outputs are then scaled by the expert probability outputted by the router. If you recall our previous diagram, the router probability is used to weigh the contribution of different experts to the final embedding, just as we did in dense MOEs. This is often also called the gating score because it gates or limits how much information can flow through each expert. Finally, the tensors are aggregated and we get our desired output embeddings, again of shape t, d. And just like that, we have learned how to replace feed-forward layers with sparse MOEs with top 2 routing. Although we spoke about top 2 routing, of course you can explore more than just 2 experts as well. Basically TopK routing, where K experts are picked for each token. People have tried other experiments as well, like the noisy router method, which adds some random noise to the router distribution before doing the expert selection, thereby introducing some randomness to promote more exploration of experts. And there are also methods where The first expert is selected according to the argmax, but the secondary experts are chosen randomly from the router's probability distribution. Most implementation of mixture of expert models also use additional auxiliary loss functions as well. For example, DeepSeek V2 uses 3 additional loss functions: an expert level balance loss that regularizes the router probability so that they are always balanced and not become too skewed towards specific experts; then a device level balance loss for multi-device training that promotes that tokens from a batch are well distributed across multiple devices to properly utilize the computational resources to the maximum; and thirdly, a communication balance loss that promotes balanced exchange of information among different devices, promoting efficient communications. Generally, these losses are weighed very less compared to the actual next word prediction loss, which is around 0.02 times of that. In the recent Mixtral of Experts paper, they did some routing analysis to figure out patterns of how routers pick different experts for different tokens. Well, our intuition might tell us that different experts will be picked depending on different domains. Like there may be one expert for math, one for code, one for language. But remember, there is nothing explicit in the loss functions to promote these behaviors. The loss function is just trying to load balance. To investigate the nature of expert routing, the researchers passed different datasets like archive papers, philosophy papers, and biology papers through the LLM and see how the experts are picked. If experts were domain specific, there should be a clear bias for some experts with certain datasets. But however, this is not true. As you can see here, the distribution of experts is pretty even despite the domain variance. The routers do exhibit some syntactic behavior. When processing code, for example, indentation on tokens are assigned always to the same expert as shown here. Also, consecutive words are often routed through the same experts as well. Also, apparently the word self in Python and question in English route through the same expert. I don't know what to do with this information, but okay. But moving away from Mixtral, let's talk a little bit more about DeepSeek again. In the recent DeepSeek V3 model, the authors were concerned that introducing those additional losses from DeepSeek V2 may negatively impact the quality of the model's performance. Instead, they removed all the auxiliary losses and used a much simpler method for load balancing. Basically, for each expert I, they introduce an additional expert bias term called BI as shown here. When selecting the TopK tokens, they add these biases to the router's output affinities, thus artificially increasing or decreasing their probabilities of being selected. Important to note that these biases are only used during the TopK selection of experts and not during the actual gating calculation. After each iteration of training, they look at which experts got selected more and decrease their biases, and look at experts that were getting selected less and increase their biases. By this way, they keep modulating the bias using this hyperparameter called bias update speed to maintain that no expert gets a huge selection advantage. No additional losses are required, just a simple load balancing method that apparently just works. DeepSeek also introduces the concept of a shared expert, which is a simple, normal feed-forward layer through which all tokens will go through by default. The authors suggest that this allows the shared expert to learn all of the common things like sentence structure and all of that, and leave more nuanced domain-specific representation learning for the routable experts. The final load balancing technique we will talk about today is the switch transformers. Each expert network is assigned a predetermined capacity. The expert capacity determines the maximum number of tokens that one expert is allowed to process. Basically, after computing the router scores, each expert fills up with tokens right up to this expert capacity by routing each token to their expert with the highest probability. When the expert is filled up to the capacity, new tokens are no longer routed to it, even if they were the highest probability ones. As you can see, with this blue token is not getting selected for this expert as shown beautifully by this red dotted line. The expert capacity can however be increased to accommodate more tokens, which generally reduces the number of tokens to overflow their assigned expert. The expert capacity when increased will accommodate more tokens, which generally reduces the number of tokens to overflow their assigned experts. But it also adds more computation to the network, as each expert now has to process more tokens. In the same paper, they proposed another technique called leave no tokens behind, and that is pretty simple as well. Basically, the tokens that are left unassigned after the first iteration can be reassigned to their second highest router. This reduces the number of discarded tokens while still ensuring that none of the experts get overloaded beyond their expert capacity. Expert capacity has evolved as a pretty popular technique these days to prevent bottlenecks in distributed training. Coding expert capacity is also pretty simple. For each expert, we just find the tokens with the maximum affinity towards them using this argmax operation. And from this list, we randomly select expert capacity number of tokens and process them through the expert network. The rest of the code is the same as TopK routing from before. Alright, that was all I had to say about mixture of experts. There is some literature where experts are applied to attention modules instead of the feed-forward layers, but we will talk about those another day. But before I go, let me summarize everything for you in some bullet points. First, the goal of mixture of experts is to route incoming tokens through multiple subnetworks within the LLM. Second, the most common way to implement an MOE is to replace the feed-forward layer with several expert networks and a router network to assign the input tokens to these experts. Everything else in your transformer code remains the same, just change the feed-forward layer with a mixture of expert layer. Third, dense MOE models are those where every expert processes every token, and sparse MOE models are those where a token is only routed to a small subselection of experts. Fourth, selecting at least 2 experts per token is essential for the network to be able to compare 2 experts and explore different options. Fifth, we talked about different ways to encourage this load balancing and exploration, like adding noise, adding biases to the selection, the concept of expert capacity, the concept of adding expert biases, as well as some specialized loss functions to explicitly balance the load across experts and devices. Lastly, always remember that mixture of experts have to load all of the experts together in the devices when the model is initialized. But when processing a single token, it only activates the experts as picked by the routing algorithm. This makes inference cheaper to run because you cut down on a lot of computation and you can process more requests concurrently because you have more free resources, more free compute to spend. Thanks for watching this episode of Neural Breakdown. I will be seeing you in the next one. You are magnificent.